Since we moved quite a bit, I will do just a little bit more and then maybe review some of the things that we have covered in preparation for Friday. If you have questions, we can discuss them, okay? So let me just talk about this just for a moment. Now, Hankel, these are approximate solutions, but when you look at the actual solutions of these Bessel function, or the spherical Bessel functions, etc., what do they look like to you? What do you think they should be like? Do you have a sense? Do you remember I talked to you about the Legendre functions? He said, I have no idea what these are, but then we figured out. Do you have an idea what they should be like? Yes or no? No. Maybe? You're thinking. Yeah. Okay, I can hear. Yes. All right. Think about what they're solutions of. What are they solutions to? We erased the equations, but there were solutions to Bessel functions. Yes, it's a second-order differential equation. Okay, and we know that if we had that approximation, it has what kind of solution? Harmonic solution. So there's something about the harmonics, but it's not a straightforward harmonic solution, except in the far field. Okay, but in the near the source, it still has this elements of harmonics. So let me write down just the first couple of terms and see what they mean to you. First of all, the one thing that they also need to include in them is the change of amplitude with distance. There's a harmonicity, meaning changing with some periodicity, but also the amplitude needs to change as it goes away because it's spherical, not like a plane wave where the amplitude is constant. So the J0, okay, that's a function of order 0, say Z, okay, 1 over Z times sine Z. So Z can be KR if this makes you happier. You know, that's okay. And you can see that that's an equation that needs to kind of change like that, right? With a straight amplitude down. Okay? And Newman equation, cosine Z over Z. So what would be the Hankel equation? Take it? Yes, there's summation, but how? Okay, so it's sine Z over Z plus I, actually in this case minus cosine Z over Z. And you can actually write this as IZ divided by IZ. Exponential, see, cosine. Let me make sure this is. So this is the first one, and the zero order, and the first order is now you can see it's getting a little bit more complicated. And the first order Neumann function is minus sine z over z minus cosine z over z squared. And from here, and these expressions, there are further expressions of these for all the higher order harmonics. In fact, there's a series expression for the Bessel functions in terms of trigonometric functions. Okay. Questions about the Bessel functions, spherical Bessel functions? If not, I go back here and erase this too. Now you have a complete solution. Okay, we have the R component, theta component, phi component. The phi component azimuthal symmetry, that was the easiest. Sine and cosine. The polar component, Legendre functions, and the distance dependence is spherical Bessel functions. Now we have gotten the solutions, yes, solutions for R, P, and phi individually, and we should be able to write the general solution for sound radiation or sound pressure in spherical coordinates. How would you do that? Okay, if you can help me, I will write it down. What makes sense here? Yes? How many different types of harmonics did we have? Number one, in those equations. And we had some constants that coupled these equations together, right? What were they? The letters. What? C and N. And C was M. Okay, so we have N and M, okay, are representing the harmonics. So you need to sum them up in N 0 to infinity, M 0 to infinity. So you have two series. So what we're doing now is writing the sound pressure. Remember at the very beginning we said we could expand this. We're writing this and we say we know the expressions, but they have, excuse me, harmonics. One from M0 to infinity, the other one is N0 to infinity. One expression, one type of expression we can use is for the surfaces, we can do, which one? The Laplace surface harmonics, spherical harmonics, okay? And that would be coefficients y of the first kind, a coefficient of the second kind. Again, the difference in these were the sine and cosine. Okay, so this takes care of the angular distribution. Okay, the next we have are the constants. And harmonic time dependence. In some ways, there aren't really 4 coefficients. You can combine them and reduce the number of those coefficients. Now, in axisymmetric problems, what do we do in the axisymmetric problems? Axisymmetric with respect to phi. M becomes 0, right? So you drop one of the series out. Are we all together? Yes? Okay. In that case, now we have a more simplified pressure expression. One coefficient. You notice now I'm writing it a little bit differently, just to point out that there is really no difference in writing either in terms of Bessel functions, Newman functions, or Hankel functions. Okay, write it, and let me explain what we're doing here. Okay. Do you remember this part? Do you feel comfortable with this? The Laplace harmonics, that was, no? You don't remember? Remember, maybe I said cosine n phi times p. And then the second part was sine and phi, the Laplace. So it was a combination of the theta and phi together, okay? And we call that the Laplace spherical harmonics. Now, if it is an axisymmetric problem, then n's drop out. You only have the Legendre functions. Legendre functions that are symmetric, okay? There's no n here, Legendre functions. That's all you have, and only one of them, because sine and cosine are dropped out. Okay, here, what is the difference between this and this expression in brackets? Nothing. Why? Combinations of these give you this, okay? If you take this expression, which is Jm plus In, and then this expression, Jm minus In, okay? And you add and subtract it, you can express this like that or vice versa. That's all it is. I write it this way just to make sure that you also notice there's no difference in how you express it, because it's a general solution, okay? And there's another reason. The next step we want to do is for axisymmetric problem, axisymmetric radiation problem. Okay, what does this mean? This introduces a further simplification. How would you simplify this? When I give you an equation like this, and I say, okay, or like this, simplify it to represent an axisymmetric radiation problem. just to represent. How would you reduce it to that case?
I will cancel the J term because it was inside radiation, the outside.
Okay, maybe. How about you, Emrullah? No idea. Okay.
Writing some terms not to the infinity.
Writing some terms not to the infinity. What is it?
Like,
Oh, you mean these? Why? Stop looking there. Listen. Use the other notebook. Why? Okay, this is, you're bringing an issue. What do these represent? M0 to infinity. What do they represent? Where do they come from? Where did we see M? Okay, so what does it mean to add these terms from 0 to infinity? What happens if you don't add them after 15? Right. And see, this is like Fourier series expansion. If you chop it off, you're not including the higher order terms, so it becomes an approximation. When you calculate, you always approximate anyway. And so it's a matter of what your error will be at the end. So that doesn't help you here. Okay, that's a different story. So, axisymmetric radiation problem. What do these terms mean to you? If something is axisymmetric, what would you do up here? Come on. What does axisymmetric mean? What does it mean? The word itself, what does that mean? John, what does axisymmetric mean? Around the z-axis. Okay. What does that represent? How do we represent that? What do we do? What does it mean? Yes?
It's not harmonic.
Okay. What is it? It's uniform around z-axis. And if it's uniform around z-axis, how do we represent it? Okay, but we have three variables, okay? Which one comes into play? Which one do we not need if it is
We don't need
phi? We don't need phi. And to do that, I don't see a phi here, but what else do you do? I'm asking you, but the others know that they don't know either, okay? So you help us. What does it mean? I just solved it right here. It's N0. What's the problem here? Axisymmetric means exactly what you described, but n is equal to 0. Emrullah, you look lost. No? You okay? Are you lost? Okay.